We usually think of computer code as, like, a strictly modern invention. We picture glowing screens, late nights, a bunch of ones and zeros creating this digital universe from absolute scratch.
Right, yeah. It's the hidden language that dictates exactly how a system is allowed to behave. I mean, without the code, the machine just doesn't know what to do with itself.
But what if the most influential source code in human history wasn't written on a computer at all? What if it was written on papyrus over 2,000 years ago, and it essentially programmed human logic itself?
That is a phenomenal way to look at it, honestly. We are talking about a text that laid down the absolute bedrock of deductive reasoning for the entire world. It's like an ancient operating system for the human mind.
Welcome to the deep dive. Today we are uncovering the secrets of a text that has fundamentally shaped how we think, argue, and, prove things to be true.
Yeah, it really is foundational.
For you, the listener, whether you are trying to sharpen your critical thinking for a big meeting, or you're just insanely curious about how the world works, this is the masterclass. We're looking at a modern translation by Richard Fitzpatrick of J.L. Heiberg's Greek text of Euclid's Elements, specifically Book 1.
Right. Book
Our
one.
mission today, to understand how Euclid, working in Alexandria around 300 BCE, built an entire universe of logical reasoning from absolute bare-bones scratch.
And just to give you some context on exactly how massive this is, Euclid's Elements is the world's oldest continuously used mathematical textbook.
Wow.
Yeah. But here is the critical thing to understand about Euclid and Alexandria. He didn't necessarily discover all these theorems himself.
Right, because the source material credits earlier Greek mathematicians for a lot of the heavy lifting, right? People like Pythagoras, Hippocrates, Zacchaeus, and Eudoxus.
Exactly. Alexandria at that time was like the Silicon Valley of the ancient world. They were gathering all the knowledge of the Mediterranean into the Great Library.
Oh, that makes sense.
So Euclid's true genius wasn't really in discovering new shapes. It was in his arrangement. He took this massive, chaotic pile of existing geometric knowledge and arranged it in such a logically airtight manner that every single complex idea undeniably follows from just 5 simple axioms.
And he did it with his hands tied behind his back. There were incredibly strict rules for this ancient geometry. Before we get to the shapes, we have to understand his constraints.
You absolutely do. You have to remember the core rule of this text. The only tools allowed in Euclid's universe are a straight rule, which is just a straight edge, not a ruler and a compass. That's it.
Just a straight edge and a compass.
Yep, you can draw a straight line and you can draw a circle. And what's even more crucial is that empirical proofs by means of measurement are strictly forbidden.
Which means no rulers with little tick marks on them. You can't just measure a line and say, yep, that's 3 inches and this other one is 3 inches, so they are equal.
Right, you are absolutely not allowed to measure. You can only say that magnitudes are either equal or that one is greater or less than the other based purely on logical deduction.
But why? Measuring is so easy.
Well, measurement requires human senses, and human senses are flawed. The wood of your ruler might warp in the humidity. The ink on the papyrus might bleed a fraction of a millimeter.
Oh, I see.
Measurement is empirical, meaning it relies on observation, and observation always contains doubt. Euclid didn't want, close enough. He wanted absolute, indisputable certainty. Logic is not flawed.
Okay, let's unpack this. Before we can build this logical universe, we need to agree on the raw materials and the rules of physics for the universe itself, right? Euclid starts Book 1 with these definitions, and I have to be honest, when I read them, they sounded bizarre. They're almost philosophical.
They really are. He starts by defining the absolute most basic concepts imaginable, basically stripping away all physical reality.
Yeah, I'm going to read definition 1 straight from the text. A point is that of which there is no part. What does that even mean? If I draw a point on a piece of paper, I can see it. It clearly has a part. It has ink. It has physical matter.
What's fascinating here is that Euclid is actively fighting against that physical ink. He is establishing pure abstraction.
Pure abstraction.
Exactly. A point in Euclid's universe is just a location. It has no width, no depth, no physical reality at all. It is purely an idea of a specific coordinate in space.
Okay, so it's a concept, not a physical dot. Then he moves to definition 2. A line is a length without breadth. Again, my physical pencil mark has width, but his line does not.
Exactly. And from those abstract definitions, the raw materials, he introduces the 5 postulates. If the definitions are the materials, the postulates are the physical actions you're allowed to take in this universe.
The actions, right.
So postulate 1 lets you draw a straight line from any point to any point. Postulate 2 lets you extend that line continuously. Postulate 3 allows you to draw a circle with any center and any radius.
And then there's postulate 5. The text actually has a really fascinating footnote about this one. It's incredibly dense.
Oh, yes. Postulate 5 is notoriously complex. It deals with straight lines falling across other straight lines and the internal angles they make.
This sounds like a headache.
It kind of is.
Yeah.
It took mathematicians thousands of years to fully grapple with it. But, as the footnote points out, what this postulate essentially does is specify that we're dealing with the geometry of flat space.
Meaning not curved space like the surface of a globe, but a perfectly flat, infinite plane.
Precisely. If you draw a triangle on a flat piece of paper, the angles add up to 180 degrees. But if you draw a triangle on the surface of the Earth, say, starting at the North Pole, going down to the equator, across, and back up, the angles add up to more than 180 degrees because the space is curved.
Wow, okay.
Yeah, so postulate 5 sets the physical parameters of everything that follows Euclid's universe is flat.
So we have the definitions, we have the postulates, finally we have the 5 common notions. These are different, right?
Right. These aren't geometric actions. They are fundamental, inescapable truths of logic itself.
Like universal rules.
Exactly. Common notion 1 states, things equal to the same thing are also equal to one another. If A equals B and C equals B, then A must equal C. It's just a universal fact.
And common notion 5, which we will definitely come back to, the whole is greater than the part. Meaning my entire car is larger than just my steering wheel.
Exactly.
So to go back to my earlier thought, Euclid is essentially writing the rule book for an incredibly complex board game. He's saying, look, if we're going to play this game together, we have to agree on exactly what a game piece is, how the pieces are allowed to move, and the fundamental laws of gravity on the board.
That's a really great way to put it.
Because you can't argue with the rules once the game starts, right? You just use them to make your moves.
That is a perfect analogy. And because you and Euclid have agreed to these unchangeable rules at the very beginning, if you follow them perfectly, the conclusions you reach later on simply cannot be argued with.
So, what is the very first move? Let's look at proposition 1. He has his rules, his empty flat universe, and he decides to build something.
Right. He has to start somewhere.
The goal of proposition 1 is to construct an equilateral triangle, a triangle where all 3 sides are perfectly equal on a single, given, finite straight line.
Oh. And remember the constraint here he has to prove it's perfectly equilateral without using a measuring tape.
I have to admit, when I first looked at this, I wanted to push back. I was reading this incredibly complex method of drawing overlapping circles, and I thought, why go through all this trouble?
It seems like overkill, right?
Totally. I mean, if I have a straight line on a piece of paper, why can't I just take a ruler, measure that it's 2 inches long, and then carefully draw 2 more 2-inch lines to make the triangle? Boom. Done.
It's the natural modern reaction. But as we discussed with the ink and the wood, if you use a physical ruler, you are relying on the physical world. Measurement contains empirical doubt.
Right, and he hates doubt.
What's fascinating here is that Euclid wants absolute mathematical certainty.
So how does he actually get that certainty? I want to walk through this because it's a beautiful trap he sets. He takes the straight line, let's call the ends point A and point B.
Okay, picture that.
He uses postulate 3, which allows him to draw a circle, to put his compass point on A, sets the width to point B, and draws a full circle.
Yep, first circle.
Then he switches sides. He puts the compass point on B, sets the width to A, and draws another circle.
Visualize that, right? Now you have 2 identical circles overlapping each other, sort of like a Venn diagram. And the original straight line is right in the middle, acting as the radius for both of those circles.
Exactly. And where those 2 circles overlap at the top, he marks a new point. Let's call it point C. He draws a straight line from C down to A, and another straight line from C down to B. He's got a triangle.
But here's the genius part. How does he know those 3 sides are equal without measuring them?
He knows because of the rules we agreed to. Based on definition 15, a circle is a figure where all straight lines radiating from the center to the circumference are perfectly equal.
Great.
So look at the first circle. The line from center A to the edge at B is the radius. The new line from center A to the top edge at C is also a radius. Therefore, line AC must equal line AB.
Right, because they're both just spokes on the same wheel.
And then he looks at the second circle. The line from center B to A is the radius. The line from center B to the top edge at C is also a radius. So line BC must equal line AB.
And here is the finishing blow. He brings in common notion 1. Things equal to the same thing are also equal to one another. Line AC is equal to the baseline. line DC is also equal to the baseline.
Therefore, line AC must be equal to line BC. All three sides are mathematically identical, no ruler required.
Boom.
It's like watching a magic trick, but all the mechanics are exposed. It's flawless. But once he proves he can make a triangle from thin air, he needs to invent bulletproof ways to argue how different triangles relate to each other.
Right. He builds these tools of argumentation. Let's look at Proposition 4 and Proposition 6.
Yeah, Proposition 4 is a critical tool. It states that if two triangles have two equal sides, and the angle enclosed between those sides is also equal, then the entire base and the remaining angles must be equal too.
Basically, if two sides and the hinge connecting them are exactly the same, the two triangles are identical.
Now I have to stop you here. The method he uses to prove this, it's called superposition, feels a bit like cheating to me.
Oh, really? How so?
Well, he literally tells the reader to mentally pick up the first triangle and apply it or superimpose it onto the second triangle. He says, place point A on point D and lay the first straight line on top of the other.
Right, he moves it mentally.
But he bans rulers because they are physical and messy, but he allows imagining picking up a shape and moving it around space. How is that a rigorous mathematical proof?
I understand the objection, totally. But what's fascinating here is that superposition isn't just wildly moving things around. It's a strict thought experiment entirely constrained by his postulates and definitions.
Okay, lay it on me.
Let's break it down. You have two triangles. You know for a fact that the left side, the right side, and the top angle of both triangles are identical.
Okay, I'm with you.
So Euclid says, mentally pin down the top point of the first triangle perfectly onto the top point of the second triangle.
Just that one point.
Yep. Now, lay the left side of the first triangle perfectly over the left side of the second triangle. We already agreed those lines are exactly the same length, so the bottom corners will match perfectly, right?
Right. They have to.
Now, what about the other side? Because we established that the angle between the two lines is exactly the same, when you pin down that first side, it physically forces the second side to shoot off in the exact same trajectory as the triangle underneath it.
Oh, wow. It literally has nowhere else to go.
Exactly. Because the angle is locked, the trajectory is locked. The angle acts like a rigid hinge.
Oh, okay.
And because we already know that second side is exactly the same length as the one underneath it, its endpoint must land in the exact same spot.
And if those bottom points land in the exact same spots, the baseline connecting them must be exactly the same length. He leans on common notion 4 here, right? Things coinciding with one another are equal to one another.
You got it. It's incredibly clever. He forces the geometry to prove itself. It relies purely on the logical constraints he's built.
Okay, you convinced me. It's not cheating.
Good. Now, if superposition is his first great method of argument, his second is even more powerful. It's the method of contradiction, which we see brilliantly displayed in Proposition 6.
Here's where it gets really interesting. Proposition 6 states that if a triangle has two equal angles at the bottom, then the sides stretching up from those angles must also be equal.
Yes.
But to prove this, Euclid doesn't just show that they are equal. He proves that them being unequal is literally impossible.
The proof by contradiction. It is a cornerstone of logical debate. You assume the opposite of what you want to prove is true, and then you follow that assumption until it inevitably explodes your reality.
All right, let's walk through this because it broke my brain a little bit. Euclid says, all right, you don't believe the two sides are equal. Let's pretend one side is actually bigger than the other.
Right, we're humoring the skeptic here.
Let's say side AD on the left is longer than side AC on the right. So if the left side is longer, Euclid says, let's use proposition 3 to chop off the extra length on the bigger side, starting from the bottom, so it exactly matches the length of the shorter right side.
He cuts it down to size.
Right. He marks a new point on the left side and draws a line across the triangle to connect it. By doing that, he accidentally creates a brand new, smaller triangle hiding inside the original larger triangle.
And this is where the trap springs.
Yes, because he then uses proposition 4, the superposition rule we just learned, to compare this new, chopped-up internal triangle to the massive original triangle.
And what happens?
Because of the rules he's already established about their shared angles and the sides he just forced to be equal, he logically proves that this new, smaller triangle is mathematically perfectly identical to the giant original triangle it's sitting inside of.
Which brings everything to a screeching halt.
Okay, to help visualize this, I was thinking about pizza. Imagine taking a single slice of pizza, running it through a series of logical steps, and mathematically proving that the single slice contains the exact same amount of food as the entire pizza you cut it from.
That perfectly captures the absurdity of the whole thing. But to understand the mechanics of why it fails, think about the lines themselves, like rigid metal scaffolding.
Okay, metal scaffolding.
If you take the massive metal frame of the original triangle and you try to fold it down to match the smaller internal frame we just built, the angles would have to snap. The metal would break.
Oh, that makes sense.
The only way the math holds up is if the smaller internal frame and the giant external frame were literally the exact same piece of metal from the beginning.
And Euclid knew that. In the text, he calls this outcome absurd. Why? Because it violently violates common notion 5, which we agreed to at the very beginning. The whole is greater than the part.
A piece of the triangle cannot be equal to the entire triangle.
Exactly. Therefore, the timeline we traveled down to get here, the assumption that the sides were unequal in the first place must be totally false. If they cannot be unequal, they must be equal.
Proof by contradiction. It is incredibly elegant.
It's just so satisfying. So by stacking these bulletproof arguments one on top of the other, Euclid transitions from proving abstract shapes to proving undeniable truths about the physical space all around us.
We see this beautifully in propositions 17 and 15, where he starts dealing with intersections and lines crossing each other.
This isn't just about triangles anymore, is it?
No, not at all. It's about the fabric of a flat universe.
Let's actually walk through the logic of these rather than just stating them. Proposition 13 proves that if a straight line stands on another straight line, it either makes two perfect right angles or it makes angles that add up to exactly two right angles.
Right, so imagine a perfectly flat horizontal line on your desk. Now imagine taking a second line and dropping it straight down onto the first line, perfectly perpendicular, like an upside-down T.
Okay, I picture that.
Euclid proves that because it is perfectly perpendicular, the angle on the left and the angle on the right are exactly identical, 90 degrees each, two right angles.
That makes perfect sense. But what if the line dropping down is slanted, like it's leaning over to the right?
That's where the logic shines. If it leans to the right, the angle on the right gets crushed, becoming acute or smaller.
Right.
But the angle on the left opens up, becoming obtuse or larger by the exact same amount. Because they are sharing that same flat horizontal baseline, the total amount of angle between them hasn't changed.
Oh, I see.
They must still add up to the equivalent of two right angles, or 180 degrees.
And building directly on that, we get proposition 15. This one proves that when two straight lines cut each other like a giant X, the angles directly opposite each other at the intersection are perfectly equal.
And he proves this using the exact logic from proposition 13.
Really?
Let's say you have your X. Let's look at the top half. You have a straight line cutting across with another line jutting out from it. As we just learned, the top angle and the right angle must add up to 180 degrees because they share a straight line.
Okay.
Now look at the right side of the X. You have a different straight line, and the top angle and the bottom angle share that line. So the top angle and the bottom angle must also add up to 180 degrees.
Oh, wow. I see it.
So if top plus right equals 180, and right plus bottom equals 180, you can use common notion one things equal to the same thing or equal to each other to cancel out the right angle entirely.
Wow.
What are you left with? The top angle must be exactly equal to the bottom angle.
That is incredible. He's like building a ladder.
Yeah.
He uses the rules to prove the triangle to prove superposition to prove the intersecting lines.
Exactly. It all builds on itself.
And all of this logical momentum leads us right into the boundaries of the shapes themselves. Which brings us to a really famous one, Proposition 20.
Yes, the triangle inequality theorem. This proposition builds on everything we know about angles and sides to prove that in any triangle, any two sides taken together are always greater than the remaining sides.
So if you add the length of side A and side B, it will always be longer than side C.
Exactly.
So what does this all mean? I mean, for you listening right now on your commute or making dinner, why should you care about a 2,300-year-old geometric proof about the sides of a triangle?
If we connect this to the bigger picture, Proposition 20 is the mathematical proof of an intuition you use every single day.
An intuition?
Yeah, it is the absolute logical proof of the real-world concept that the shortest distance between 2 points is a straight line.
Because if you have a point here and a point there, the straight line is the base of the triangle. If you deviate from that straight path, if you go up to a third point and then down to your destination, you have walked the two other sides of the triangle.
Yep, you took the long way.
And Euclid just logically proved, using an unbroken chain of reasoning all the way back to a simple dot on a page, that those two sides added together will always be longer than the straight baseline.
Precisely. You already knew the shortest distance was a straight line. You intuitively understand that. But Euclid doesn't care about intuition.
He cares about undeniable certainty.
Exactly. What he is really teaching us here isn't just about shapes. He is teaching us how to think critically. He is showing us how to take complex, messy realities and distill them down into undeniable, step-by-step logical arguments that cannot be refuted by anyone, anywhere.
Let's pull all this together. We started with the absolute simplest abstract ideas, a dot with no parts, a line with no width.
Just pure thought.
Right. And we agreed to a strict set of rules where measuring with flawed human tools was completely outlawed. And from that empty universe, we watched Euclid use overlapping circles to force a perfect equilateral triangle into existence.
We saw him invent the tools of logical argumentation, moving shapes in his mind with the strict physical constraints of superposition.
And destroying false assumptions using the proof by contradiction, mathematically proving that a part cannot equal the whole.
Right.
And finally, we saw how stacking these undeniable truths results in a mathematical framework for the reality we live in, proving definitively why a straight line is the fastest way to get where you're going. It's an absolute masterclass in how to build a flawless argument from scratch.
It truly is. But this raises an important question, and it's a thought I want to leave you with today. We've only been looking at book 1.
Oh, right. There's way more.
The introduction to our source text mentions that this is just the beginning of a massive 13-book epic. By the time Euclid gets to book 10, he is attempting to mathematically classify incommensurable or irrational magnitudes.
That sounds intense.
It is. He uses something called the method of exhaustion.
The method of exhaustion. What is that?
It is incredibly rigorous. He calculates the area of a shape by inscribing a sequence of polygons inside it that continually increase in size, essentially exhausting the space. The text notes that this method is actually an ancient precursor to integration.
Wait, integration, like calculus?
Yes, calculus, in 300 BCE.
That is mind-blowing.
Using nothing but a compass, straight edge, and a few basic common notions about equality, Euclid laid the geometric groundwork for modern calculus. So the question for you to mull over is this. If Euclid could build the foundation of higher mathematics from scratch using only a handful of unarguable definitions, what massive complex problems in your own life or work could you solve today just by stripping them all the way down to their most basic, undeniable truths?
Start with your source code. Figure out the rules of your board game. Because once you find your undeniable truths, the rest is just logic.